At the heart of every atom lies its nucleus. This is the nucleus. It's tiny, but it is incredibly dense. It is made up of protons and neutrons. It is so tiny that if you assume the nucleus to be a pea, then the atom would be larger than the size of a football stadium. Now, this nucleus, it holds the atom together. However, this nucleus is not always stable. In fact, some nuclei are so unstable that they undergo a process called nuclear decay, a transformation that allows them to become more stable. After the nuclear decay, the nucleus becomes more stable. But what exactly causes a nucleus to decay? Why are there different types of decay, like alpha decay, beta decay, and gamma decay? The answer lies in the delicate balance of forces inside the nucleus. Protons and neutrons, protons and neutrons, they are held together by strong nuclear force, which is one of the most powerful force in nature. But protons, which are positively charged, also repel each other due to the electromagnetic force. Due to the electromagnetic force. And for some nuclei, this causes an unstable balance. There is this strong nuclear force which is trying to keep them together, but there is this electromagnetic repulsion that is trying to push them away. So that for some nuclei causes an unstable balance. And this is where these nuclei must transform to become more stable. And this transformation is what we call as nuclear decay. Now the obvious question is that why some nuclei emit alpha particle, why some emit alpha, while some emit beta, and some gamma rays. And to answer this, let us understand the nature of forces inside the nucleus. The nucleus has two kinds of forces. One is the strong nuclear force. This is our strong nuclear force, right? Now, the interesting thing about the strong nuclear force is that it has a very short range. It has a very short range. Now, what does that mean? That if the nucleus becomes larger, then the strong nuclear force would not be able to attract enough. And that's where the repulsive forces, because of the electromagnetic repulsion, they start dominating. This is where the repulsive forces start dominating. And this makes the nucleus unstable. Now, the nucleus would try to do is it would try to ensure that it reaches an equilibrium position where the sum of the two forces is zero and there is no instability inside the nucleus. So, if you look at the helium atom, what you would see is that the mass of the constituents of the helium atom, the mass of the constituents of the helium atom is actually greater than the mass of the helium itself, is actually greater than the mass of the helium itself, which means that there is some mass defect. And this mass defect is actually turned into energy using Einstein's famous E is equal to mc square equation. So, what is basically making the formation of helium energetically favorable is this released energy, which is called binding energy, which is called binding energy. And if you divide this energy by the number of nucleons, then this is called binding energy per nucleon. The stability of the stability of any nuclei, this is the nuclei. The stability of any nuclei can be explained using binding energy per nucleon. Apart from binding energy per nucleon, the neutron to proton ratio also determines nuclear stability. This is a plot of neutron numbers versus proton numbers for all the known nuclides, whether they are stable or unstable. Now, in this plot, if you see, the stable nuclides are actually shown in red. The region that is defined by these stable nuclides is known as zone of stability. And if you can see, there is another line which is drawn. This line is the line of n is equal to z. And what do we see? That as this n is turns greater than 15, the zone of stability gradually moves above this line. So as you can see, it is moving above this line. And this is easy to understand because as the size of the nucleus is increasing, you require more neutrons. More neutrons are required. More neutrons are required than protons. And that is because uh, the electromagnetic repulsion is increasing. However, the strong forces, since they have a very short range, would not be able to counter that electromagnetic repulsion. So you need more number of neutrons. Okay. Now each side of the zone of stability nuclides, as we can see, are unstable. Above the stability line, above the stability line, the nuclides are the ones that decay by beta minus decay. So why does beta minus decay happens? It happens when a nuclei is neutron rich, and hence they need to convert a neutron to proton, and hence they need to convert a neutron to a proton, right? Now, if you go below the stability line, then you would find nuclides which are proton rich, and they would have to convert protons to neutrons. And there you would need beta plus decay. For example, carbon 14 has more neutrons than it requires, and hence it would convert one of its neutron into a proton, as you can see over here. One of its neutron, as of now it has 8 neutrons. So one of the neutron turns into a proton by emitting a beta particle and an antineutrino. Similarly, if you have sodium 22, then it has more protons than it requires to stay stable. So it would turn this proton into a neutron by a positron emission along with a neutrino emission. Okay, now what happens at high n and z values zone where n and z are really high? At this, the binding energy per nucleon is is not really high. And what do you need over here is that you want your binding energy per nucleon to increase. You want your binding energy per nucleon to increase. And to do that, what you do is that you decay alpha, via alpha decay. And this changes your both Z and N at once. And more importantly, they reduce your binding energy per nucleon. For example, over here, what you can see is that radium is turning into radon by releasing an alpha particle. Finally, the rays that are not deflected by a magnetic field, but that are easily detected by their interaction with atoms, the gamma rays. Energy of nucleus is quantized, let me write quantized, yes, quantized. Energy of nucleus is also quantized, exactly in the same way as energy in atoms. Now, if this is true, then after alpha or beta decay, the nucleus could be left in an excited state. What does that mean? The nucleus after alpha or beta decay could be in an excited state, an excited nucleus. Why? Because energy is quantized. And that means that to come down to a stable state, it will have to emit one or more photons to, to gain stability. And because the binding energy of a nucleus, and because the binding energy of a nucleus is much higher than that of atoms' electrons, binding energy is much higher. Binding energy of nucleus is much higher than that of atoms and electrons. The energy differences between states are also likely to be much larger. As a result, the energy of the emitted photons is much larger and gamma decay happens. As you can see in this example, that we had boron 12, which decayed into carbon 12, but carbon 12 was in its excited state, and to come down to its ground state, it had to release a gamma photon.